So I'm going to do that again today. Let's see. There we go. All right. So I had a question from a student who was working on homework 4 and was having difficulty using the diff test procedure. Has anyone else encountered error messages in trying to use diff test with the virtual machine? Yes, Jenny, you have. How did you solve them, or have you solved them?
Yeah, I solved it by I put a path of where the file was.
With the
And
file
that,
that you're trying to save?
so instead of if I put the pathway to where I was saving it in both, like before I ran it, or the one where it saves it and then the one where you have to extract it. And that seemed to work.
Okay, that's good to know. I haven't tried that one yet. So yeah, if you run into problems with the save data command in particular, seems to be generating errors for some of you, but not all of you. And unfortunately, the IT people and the M Plus people will not give me access to your virtual desktop because they say it's for students only, despite the fact that I am training 25 new customers for them. Not that I'm bitter or frustrated. So I cannot help you troubleshoot any more than just asking you guys for what has worked. So I apologize for the confusion. This is the first time that I've tried to teach using the virtual desktop for M+. I have never encountered these errors in any other setup that I've had people running it in. So this is all new territory. But so trying the path on save data and on analysis for diff test. That I got a couple people saying yes, it looks like that's working. Thank you for the tip. That is helpful to know. All right. How about other questions? Anything on homework at the moment or individual data analyses for homework 5? Not yet. That's fine. I just thought I'd ask. We were talking about ordinal data last time, and we'll be finishing up a couple other models for categorical data today, and then changing gears. I have put up lecture material for the next 2 weeks, invariance analysis. So we're going to be doing it in both a CFA framework as well as an IFA IRT framework. So there are 4 total examples to go through over the next couple weeks for those. And those models will be the topic of your very last homework. So I hope to get that up within the next week or so, and it's not due until the end of finals week. But I'm trying to make it so that you could actually be done with this class by the end of the class semester. So everything will be up ahead of time. That way you can just sign out. Question for you. In terms of a schedule, the Tuesday of Thanksgiving break, we don't have class. The university is supposed to be not having classes anytime that week, but I was thinking about having office hours on that Tuesday instead of class because you have homework 5 due after break. You think that that would be useful? There's at least one thumbs up, one nod, another one. Okay. Well, tell you what, I will update the syllabus to put that on there. I'll just sit inside my Zoom from about 12:30 to 4:45 because that's the time that I would normally be teaching, and I'll open it up to both classes. That way, if you want to come by and work or ask questions, you can. And if you want to take the week off, that's your choice. So, okay, that's helpful. I will do that. All right, then do we want to look back at the M plus stuff we left off with last time? All right, so you'll get a chance to practice these models in your homework 4 and homework 5. Just to remind you sort of the high points, the magical command right here, categorical. What happens when you include that option under your variable section? What is happening behind the scenes when you denote your variables as categorical? I'm watching the chat window, or you can talk. Your choice. What happens when you say you want these outcomes to be categorical? Generate submodels automatically. Yep, automatically generates the submodels. 2 people with the exact same wording. What are the odds? Yeah, why do you need submodels? What do the submodels do? For each intercept, yeah, for each threshold actually, but yeah, it's the idea of dividing up your outcome possibilities, each category, into a series of binary distinctions. So you need submodels because you are not assuming a linear relationship of the trait predictor for your outcomes. You're allowing a nonlinear logistic relationship within each submodel. So if I have, say, 4 outcomes, how many submodels do I need? Yeah, 3. So M plus in the categorical option here figures out how many submodels you need for each item and fits them automatically. So it's either going to fit a cumulative logit model, link equals logit, or a cumulative probit model. And the difference is just a question of scale. So the coefficients for a probit model are going to be smaller by a factor of about 1.7. So long as you're using full information maximum likelihood, you can choose logit or probit. But if you're using WLSMV, the limited information option, which we're going to take a look at today, then you're stuck with probit. So these are for categorical is somewhat of a misnomer because it really means ordinal. If you have outcomes that are nominal instead, then you actually need a different command, which is nominal instead of categorical. So categorical is not a good label for this. It means ordinal specifically. So the specification of factor loadings looks the same in an ordinal model or not an ordinal model. So we tell it what the name of our factor is and which items load on the factor. We have to tell it how the model is going to be identified. So in this case, I have labeled the factor mean and variance. I temporarily made it look like they're free because over here in model constraint, I'm fixing the factor mean to 0 and the variance to 1. That way I can refer to factor mean and variance in the formulas that give me B difficulty values out of my thresholds. Do you remember what I told you about listing the thresholds? Do you need to write these all out? No, emphatic no. Yeah, don't. Not only do you not have to, but don't, because you have to know how many each item needs in order to write them all out successfully. And if you refer to one that's not possible because you didn't have data observed in one of your categories, it will throw an error and not run at all. So it's more work to write them out than is needed. The only situation in which you would need to write them out is if you want to compute difficulty values out of your thresholds, which is what I've done in this example. But if you don't need to do that, then don't go to the trouble. For binary 2, I'm assuming that question is about the categorical. Yeah, so binary variables go on categorical as well. It just means there's only one threshold. So you can still think of them as ordinal. There's really no distinction to be made in binary, but it's a special case of ordinal where there's only 2. All right. And so all of this stuff over here, you don't need to do for every single model. I would only go to the trouble to get difficulty values for the model that you decide that you want to report and interpret. So we looked at, for instance, how to test whether or not you want a constrained version of the graded response model. That's what this is. By constraining all the loadings to be equal. Comparison of fit by doing -2 times the difference in the model log likelihoods suggested that 2PL version, the version where each item gets its own slope, was a better deal. And so then we looked at the solutions. So the IFA solution in terms of loadings and thresholds is what is given in M+. So you get that whether you want it or not. That is how the model is phrased. And so factor loadings are giving you the change in the logit or probit, whichever scaling you're in, for a 1-unit change in theta. And so that is why having a theta that has a standard deviation equal to 1 is a helpful scaling in terms of interpretation, because that way a unit change in theta corresponds to a standard deviation. Thresholds then, these things give you a sense of what to expect in terms of a predicted response for an average person. So these are the low jitter probit of the lower category when theta equals 0. And if we take these times -1, that gives you your intercept. So this whole column over here, the right-hand side of this page, that is what the extra code over here under model constraint gives you. So the IRT parameters that are shown in this output are not given to you unless you have to do the math to get them. So this is different in how M+ treats binary versus ordinal. For binary items, it automatically gives you the A's and B's that go with the IRT version of the model, whereas for ordinal data, it does not. And I don't know why that is, but it's still the case in the current version of M+. And so I wanted to give you a means by which to get them. That way you can get the standard errors that go with them. So if your factor variance, is 1, your loadings are the same as your discriminations. And otherwise, the formula for difficulties is as the threshold divided by the loading. I think that sounds right. I'd have to double check. I don't memorize formulas as a general rule, but the ones that I've done enough. Yep, that sounds right. So I've got an Excel sheet where I have calculated these using the factor model parameters. That's what I'm referring to here. All right, so we went over most of that last time. We haven't looked at the pictures yet, though. Are there any questions about the model parameters? Any of that you want to hear again or hear differently? So at this point, do we know how well this model fits? Have we looked at any indication that would tell us whether or not these items are consistent with a single latent trait? Nope, not yet. Not yet, exactly. We're going to look at the WLSMV solution to get traditional fit statistics relative to a polychoric correlation matrix. So that's coming up. All right, so here's some pictures. These pictures were made by M+. These are what's known as category response curves, and they show you what the probability of each possible response option is as a function of the trait given the model parameters. So item 1, for instance, it has a loading/discrimination of 6.8, which is really high, and that translates into these clearly delineated categories. So the lowest option is the most probable up until you hit a theta of about -1.5, at which point the second option becomes most likely until, let's go with -1 or so, and then the third option, and then the fourth. So the ones on the end here, so the red line that extends up to 1 and the black line that extends up to 1. The reason that those go up to 1 and stay there is because there is no further option. The model predicts that people with a theta of positive infinity are going to answer category 4 because there is no other category above them. So it's not really as precise as the picture kind of makes it look like. It's because there's no other alternatives that are below category 1 or above category 4. So this item is concentrated in a range where about -2 theta to about 0 theta, that's where these categories start to transition from one another, versus, say, this item over here. This is item 7 that has a slope of 1.7. And you can see that the categories are a lot less steep here. The middle kind of gets squished together in the items that have a lower slope. They're less differentiated. And this one is concentrated even lower on theta. So a theta of about -3 up to about, -2 or so. So this is not a great item where it is. This one is a better item relative to the two. So the steepness of the curves is indicative of the size of the loadings or the discriminations. So if we look at all of the items information curves, these are pictures I made in Excel because I liked my version of the pictures better than what M+ gives you. This is item information for each of the items. So how much the item contributes to the measurement of the trait. And these curves are a lot wider than what we would have seen for binary items because each item has 3 separate submodels. So an item that has 4 choices is likely going to have more information than an item that has 2 choices because it can cover a larger range of the trait. And if we sum all of these curves together, we end up with the test information curve as it's known on the right here. So test information is the analog of reliability. To convert it to what reliability is, it's information over information plus 1. And so that picture is right here. So for whom are these 7 items going to be useful? What kind of person is going to be well measured by this instrument? What do you think?
Would it be like lower to mid ability?
Yeah, anybody from about, if I use 0.8 as sort of a conventional cutoff, like a theta of -2-ish over to a theta of about 0.4 on the trait. So low to mid people have a decent level of reliability. But after 0.4 on the theta scale, reliability tanks. And that is a direct consequence of where the item's difficulties lie. So I have a picture that I made that tries to combine the IRT A and B parameters. So the top half of the picture has the A for each of my items, and the bottom half has the B values. So B values are item difficulties. That is the amount of trait needed to obtain a low jitter probative 0. So 50-50 probability of the higher option of the two. So for instance, the first item, the red dot here, means that it takes a theta of -1.5 to transition from can't do it to big problems doing it or higher. And the orange triangles mean at a theta of -1, we transfer from can't or big problems up to some problems or can do it. And I'm wording it this way because the whole model is cumulative. Remember, it's like 0 versus 1, 2, 3. That's the reds. 0, 1 versus 2, 3 is the yellow oranges. And 0, 1, 2 versus 3 are the greens. So each submodel uses all the answers. You can think of it as transitioning to something greater than the lower category. So red is moving off of can't do it, orange is moving off of big problems, and green is moving off of some problems, which means can do it. So a couple things here jump out at me. One is the location overall of the items. So the green, the top of the discriminate or the difficulty values here, none of them is above a theta of 0. That means that people who have above average ability have no choices to make for these items. They can do everything.
I have a question. You were saying like the green is what it takes to go from the big problems to some problems. For the red, I thought you said it takes a theta of the 1.5 or negative 1.5, I'm not sure if it's absolute, to transfer from going from can't do it to big problems. Did I hear you wrong? Because I'm not sure where it starts.
It's possible I said it wrong. So let me try to say it correctly, and we'll determine if I said it wrong or if you heard it wrong.
Okay.
These are not absolutes. So
Okay.
so -4 means 4 standard deviations below the mean. This red dot is located at -1.5. So somebody who has a theta of 1.5 standard deviations below the mean, so a low ability person, that is the point at which they have a 50-50 probability of transitioning from the lowest answer, which is can't do it, to something greater than the lowest answer. So the scale here is can't do it, big problems doing it, some problems doing it, or can do it. So red is where they switch from 50-50 probability of can't do it to something greater than can't do it. Okay, does that help?
Okay, it does. But then how do you, I guess where I'm confusing it in my head is the interpretation difference between the red dot at the lower end versus the square at the top. Because that the square at the top would be good. Or which one am I? I don't know. I'm not sure.
Yeah, I'm laughing because this is why I hate this model. I think I said this like 2 or 3 classes ago. I hate this model. It is a pain in the ass to explain. And because you don't want to interpret it in the cumulative way, you want to talk about moving from a 0 to a 1 and then from a 1 to a 2. And that is not this model. That is the partial credit model, which is the next one we're going to talk about. So I hate this, and I feel your
I know I am
frustration.
confused. It's because I'm confused because there's like nothing below the red, but we're able to interpret the red. However, there's nothing above the green, so it's confusing on how I'm able to interpret the green.
Okay.
It seems like we were interpreting from bottom up. Did I explain why I'm confused correctly?
So the green is the last transition. It's the point at which you have a 50% probability of being in the 0, 1, or 2 lumped together versus 3.
Okay.
So the lumping is the key, I think. The 50-50 split is the categories lumped together. So green is the point at which you are 50% likely to say 3, which means you can do this.
Okay.
So for item number 1, that happens at a theta of like minus close to 0, we'll say. So a person with a theta of 0 has a 50% probability of saying, yes, I can do this with no problems, which is the highest category.
Thank you.
And the point that I was making is that if I'm somebody with a theta of 1, like look at my y-axis here, it stops at 1 because I didn't need to go further because none of the items are above that. People with a theta level that's average can do all of these things. So they answered 3 to all 7 items, and I have no idea how able they are because I don't have a measurement for that. And that's why my histogram looks like this. So I have a giant ceiling effect because these are people who answered the highest response to all 7 items. And this is a great example of how statistics cannot save design. Right? Like I might see this frequency table, like I run proc-freq in SAS or I run frequencies in SPSS and go, oh shit, it looks like I have a giant ceiling effect. What if I put this into my IRT machine? Is that going to fix it? And the answer is no, because there's no information here with which to distinguish the people who said they could do everything. So the where the items are in terms of their difficulties directly creates this information or reliability function. And that creates this pile on the right-hand side of people who cannot be distinguished. They don't have any choices. So we would need to add more items that would cover the space above the green. So can train for a marathon, right? Or we would need to extend the categories to something above can do it. I do this all the time, maybe, would be a higher response. Something like that. So the location of these things is somewhat problematic because it's relatively constricted. In looking at the loadings, If I were trying to reduce items, I might be tempted to get rid of item 7 because it has the lowest loading by a considerable margin of the others. Now, do you think that would be a good idea or a not so good idea? Should I dump item 7 because it doesn't have a good loading?
I think it depends on what the item is, right?
Item 7 is answering the phone.
I
Oh,
think you need it because otherwise you don't have information about those people at that trait level.
Yeah. I would say if I don't want to measure anybody below 2 standard deviations, I don't need it. Like if I'm okay with having a floor effect, then I could get rid of this item. But this is my only shot at differentiating amongst super low people, whether or not they can answer the phone. And I think, by the way, for those of you who've never seen phones that were plugged into a wall, that would entail like getting out of the armchair or off the couch and physically walking over to the wall in time to get the phone before it stops ringing. I think that's what the item is measuring, not just the physical act of picking up the phone. I don't know about you guys, but my phone is always within item's reach, right? So I'd have to be in very bad shape before I couldn't answer my phone. But please don't tell my mom that. When she leaves me voicemails that say things like, "Oh, I guess you're not home." Like, no, that stopped being a thing in 2001, Mom. Not being home. I'm just not listening to you. I didn't feel like answering your questions today. I'm sorry. But anyway, answering the phone is a way to distinguish amongst super low people who can or can't do this item. And so, from that perspective, it would be useful, even though it's not that useful in that area. It's all we got in that area. The proximity of the oranges and the reds makes me think that can't do it versus big problems doing it are not separable enough. If I were going to entertain different sets of response options, I might try something that makes that further apart. So those are sort of collapsed onto each other in a lot of these items. The distinction between green and orange is a little bit bigger in some of these. So, all right. Thoughts or questions on this much? All right, then let's see what the same process would look like using the other estimator. So a much more straightforward way of assessing absolute model fit is to switch. So the differences in terms of the syntax is right here. Going from estimator equals ML, link equals logit, to estimator equals WLSMV, which stands for weighted least squares with a mean and variance corrected chi-square. The parameterization equals theta makes it so that it translates into a probit IRT model. The residual variance is 1 in this parameterization. So switching those means it's going to do what for me behind the scenes? What am I asking it to do besides just fit the factor model? It's going to do something first. Something correlation? Yeah. Make a covariance matrix? Yeah. Yes, for binary items, it's called a tetrachoric correlation. For ordinal items, it is called a polychoric correlation. And yeah, it's going to estimate based on the data what the full correlation matrix would be across your items. So it's coming up with an H1 model first based on your data, and then it's going to use that as a comparison to see how well your HO model fits that saturated matrix. Is polychoric the same as Pearson? Thumbs up for yes, thumbs down for no. Is polychoric the same thing as a Pearson correlation matrix? What do you think? One vote for no, a lot of abstainers. Yeah, the answer is no. Pearson correlation is not the same thing as this. This is trying to come up with a correlation that would be consistent with a bivariate normal distribution for each pair of items based on the two-way contingency table of their responses. That's a mouthful, but just to say that no, this is not your first year statistics covariance matrix. And it's confusing because there are a few other instances of correlations that are the same thing as Pearson. So for instance, if you have you heard of a phi correlation? That's a correlation between binary items. That's Pearson correlation. It's the same thing. It's just a computational shortcut. Likewise, I think point by serial. Am I saying that one correctly? That's binary with quantitative. That's a Pearson correlation that has a computational shortcut because of the forms of the items. These are not. So the idea of using tetrachoric or polychoric correlations is to try to solve some of the range restriction problems that pop up in using Pearson correlation as a measure of association. So for instance, for two binary items, the only situation in which the Pearson correlation could be 1 between two binary items is if both of them have a mean of 0.5. Otherwise, if their means are skewed, that's going to limit the possible correlation they can show. And the same is true to a different extent for ordinal items. There's a limited amount of variance that they can have and a limited amount of covariance. And so the use of these alternative measures of association are a way to try and combat that problem. It's not technically correct, but I think you can think of these as like the correlation among the probits of the responses. In my head, that's sort of the way I abbreviate this idea. It's in the link. It's not just from the observed data, but it's a bivariate measure of association that's going to become the H1 model. That's the important thing. So in this method of estimation, it doesn't matter how many thetas or factors you have, it will go just as fast. And you get this comparison of H1 versus HO that gives you all the usual fit statistics. Now, do you remember what the caveat is? What's the one bad thing about this that you want to be careful about in using it in practice? In what situation would you get different results? Not just because of estimation, but because of something else from a full information. Yeah, missing data. Yeah, data. Random versus missing at random versus missing completely at random. So anytime that you start with a summary of the data and you do your analysis on that summary, such as when you're summarizing with the polychoric correlation matrix, missing responses are assumed completely at random, which is exactly what it sounds like. Like there's no reason what they would have been has nothing to do with the data that you have. Whereas full information approaches, where you're reading in all the individual item responses and you're fitting the multi-way contingency table of all possible response patterns as the thing you're trying to approximate, that's full information maximum likelihood. That is missing at random, which means random conditional on the other information you have about the people. So that's the situation. Missing data is where you can't just rely on this for everything. That's the caveat. There's a whole lot of literature looking at whether or not diagonally weighted least squares, the WLSMV, does a good enough job versus ML. And the literature is somewhat inconsistent, but it depends on what you're claiming is good enough job, and it depends on your sample size. I think in smaller samples, WLSMV may do a better job than full information maximum likelihood. But like I said, there's a whole bunch of studies on that, and you can look those up. My job is to teach you how to estimate both of these ways. That way you can get some indication of fit, which is why we're doing it this way. So those two lines right there, that's the only way that this differs. That's it. The way you specify factor loadings, the way you would specify thresholds, the way you identify your model, everything else is exactly the same. You just switch the estimation method. And so the rest of these then show you how to make the IRT parameters the same as before. And on the left-hand side is the fit of the model that has separate slopes. So RMSEA is not very happy with this model, but CFI and TLI and SRMR are. So by at least some of our criteria, it looks like it fits reasonably well, although it doesn't fit perfectly given the significant chi-square. The other thing that's in this output is a comparison using diff test to see whether or not we can constrain the loadings to be the same. So just as an example of a nested model comparison. So to review how to do that specifically, the model that has more parameters in it has to be estimated first. Order matters. So the model that has a separate loading for each item, for instance, on the save data line, it's diff test equals, and then you put the name of a file there. So it ends in a .dat extension, but you can name it whatever you want. And we just learned earlier today that if you put the path to where that file is, M+ does not throw an error message, at least for some of you. So we're running the model with separate slopes. It is saving information about this model to be used in conducting a model comparison for us. The saved information goes on the analysis line of the nested model, the one with fewer parameters. So the 1PL version of the model is being estimated. It's going to read in the information from the comparison model. And then if you did it correctly, you should get this extra piece of output right here, chi-square for difference testing. That is the result of the diff test command. So the difference in fit between models gives us a chi-square of 93 on 6 degrees of freedom. That is highly significant. So the 2PL model with separate slopes fits better than the model that constrains all the slopes to be the same. And here are the parameters from that model. The loadings and everything else, they're in probits instead of logits. So that's why the numbers are different, in addition to differences concerning the missing data. So these are the expected z-scores that go with the probabilities for the area to the left under the curve. And here's some words. So I described the process differently than what's actually in the handout. I described fitting the model using WLSMV to check absolute fit, and then refitting it using ML to get those versions of the parameter estimates in logit scale. So that's what I'm asking you guys to do in homework 5, which means that you can start with this text as your template for homework 5. I am fine with that. But if I see the words like activities of daily living in your homework, what's going to happen? Grumpiness. Grumpiness, yeah. I get very grumpy. So go through with a find and replace and make sure that whatever names of the variables that I have are not the names of the variables that you have. Otherwise, you can borrow my words as a starting point. That is fine with me. All right. So any questions on any of that? So at this point, you should be able to finish homework 4. And if you choose this ordinal model for your homework 5, then you can do that as well. Otherwise, I've got a few other models that I can talk about. So I'm going to dig back into lecture 6. This is slide 14 that we've talked about a few times. It's a good place to start. Let me move the thingy out of the way and talk about some other models that you may come across. So the graded response model, that's what we've just been talking about. The idea of using binary submodels that are cumulative such that all categories get used in each binary submodel. That has a lot of parameters. So each item has as many parameters estimated for it as it has categories. Because if I have, say, 5 categories, that's 4 thresholds in one loading. So 5 parameters for 5 categories. If I had 6 options, that would take 5 thresholds in one loading. So one of the ways that people have come up with to try and save parameters to make it more parsimonious is what's known as a modified graded response model or a rating scale model, depending on who you read. And the idea behind this model is to constrain the relative distances between the categories to be the same across items. So it's parameterized a little bit differently. Each item has a B value that describes its overall location, and that's separate across items, as well as potentially a separate A, although I think in many sources they constrain A to be the same too. And then we have these C things. These are like category shifts, and there's no I after them because they're constrained to be the same across items. So it'd be like relative to the general location, how far away is the 0 answer? How far away is the 1 answer? How far away is the 2 answer? And so they constrain those to be parallel. I have a admittedly crappy picture, but hopefully it will do the job of illustrating the idea here. So the top of the slide here on 16 is trying to illustrate what this modified model is doing. It is assuming that the distances between the categories are the same across items. Whereas in the bottom, this would be a typical graded response model to where the distances between don't have to be the same across items and they don't have to be equidistant. So this model, I think you could trick M+ into doing. You'd have to do some constraints. I've tried to do a version of that. I can give you an example if you're interested, but you may find this programmed into other packages more directly. So those of you who are familiar with FlexMert or models in R, do they have this one in there? Yes, they do. Okay. So you've seen this before. So this is another instance in which it doesn't have to be all or nothing. You could have some items have the categories constrained to be equal across those items, but then have other items not. There's nothing that stops you from customizing your model to constrain what's possible and not constrain what's going to hurt fit. So in terms of summarizing ordinal categories, these are the names that go with it. For whatever reason, these models tend to have separate slopes as a default. So I've given you sort of 2PL-ish versus 1PL-ish as ways of thinking about it, but that's not what they're called. So we have the graded response model, which corresponds with cumulative logit in the cell where we have different slopes for different items as well. So I think this family is one of the more common ones, but there are others for categorical data that you will see, and so I wanted to get a chance to talk about those. So any questions on that before we change to the next one? Okay, the next one. I like this one so much better. This is a partial credit model. So this one corresponds to what we would call an adjacent category link in generalized models. And it still has C-1 submodels, but they're made in a way that makes more sense. So rather than 0 versus 1, 2, 3, for instance, it's 0 versus 1, and then 1 versus 2, and 2 versus 3. So it's going to model the probability of the next category relative to the previous at each point along the response continuum. This model is popular with Roche people because the default version of the partial credit model constrains the slopes to be the same across items. So it is a Roche model. So if Roche people would estimate, say, a 1PL for binary data, for ordinal data, they would go to this one, the partial credit model. If you want to allow different slopes across items, so the 2PL version of this, that is what's known as the generalized partial credit model. So it looks like this. So I've got the IRT version on the top and the IFA version on the bottom. And this model was recently implemented in M+. The parameterization of it is somewhat confusing. So if you're going to fit this, I may need to help you because I don't have a great example using this type of model in M+ yet. But the key thing is that each of these submodels is expressing a conditional probability. So the traditional way of writing the partial credit model to me is horribly non-intuitive and difficult to understand. So I've come up with a version that is much more direct. So within each of the submodels, like if you answered, say, 0 or 1, so you're conditioning the data just down to those two categories. The job of the submodel is to give you the probability of the higher of the two. So if you answered 0 or 1, what's the probability that you answered 1 as a function of the item's discrimination, your theta for the subject, and this thingy right here, which is a delta term. It's like difficulty, but it's not the same. It is a measure of location. What delta tells you is the trait level at which the next answer becomes more likely. Not necessarily 50% though, just more likely. So where the category response curves cross, that's what delta tells you. And each submodel has a different delta. They all share the same A. So the difference in the partial credit model that we're looking at here versus the previous graded response model lies in the definition of these binary submodels and what the probability is referring to. It's a conditional probability of a subset of responses for each of these. And M+ still prints thresholds in the output. It labels them as steps, but they're still thresholds. And it took me a while to figure that out, and I was very angry with them for relabeling something with a new word that they didn't need to. But it's a threshold. That's what it's telling you. So the key thing about this model is that it doesn't assume these categories are ordered. There's nothing in the model that says that these deltas, like delta 2 has to be bigger than delta 1, or that delta 3 has to be bigger than delta 2. It's only adjacent. So let me show you some pictures here. This is what an example of the generalized partial credit model could predict. So this is for an item that has a discrimination of 1. And this picture looks like it could have been generated by the graded response model in that you have the probability of each answer as a function of theta. But look at this over here. I'm pointing at my computer monitor like that doesn't help. Do you see my giant pink arrow? That thing right here. So the first delta in this model would be if you answered 0 or 1, at what theta does 1 become more likely? So I've used color here to try and give you the transitions between the two, but delta 01 would be at a theta of like minus 1.5-ish, right? Where the blue line and the pink line cross. That's what delta means. It's the trait level needed to kick you over into the next category. So if you answered 0 or 1, that first submodel gives you the probability of the 1. The next one then would be the probability of a 1 or a 2. But look at what happens. 1 and 2 are pink and yellow. They cross clear back here. So delta 1, 2 is actually lower than delta 01. It takes less ability to pick 2 instead of 1 than it takes to pick 1 instead of 0. That sounds messed up, huh? So when would you see something like this? I can think of 2 instances. If nobody really picked 1, then you will see reversals like this. That's what it's called. If one of the categories is not used very much. And the other is that you're wrong about order. So, for instance, if you think of like a problem that a kid would do, say, in an elementary school math class where it takes multiple steps to solve a problem and you want to give them partial credit for how many steps they got complete, steps later in the chain might actually be easier to do than steps that were earlier in the chain. So you could be incorrect about the relative orderings of these things, and that could show up as a reversal. So the partial credit model, in addition to being more directly interpretable as the transition between each set of categories, is a way to empirically test whether they're actually ordered. So if you think there might be an order but you're not sure, this is a way to look at that. Yeah.
This is what a lot of my data looks like, and one way that it was explained to me is like, I think they were trying to avoid this because they said that like if there's no, like each of those lines needs to be like the highest line at some point on the theta. So like for example, that pink one is never like higher than the other lines at any point, but like yellow is highest at a theta of -1. I thought that there was an answer where like one solution would be to combine categories. Like, for example, just take the, I guess that would be answering one out so that that pink line doesn't, is just like put in with one of the other categories. Do people do that? Is that true?
I think you could do that. Which category you dump it into, one might argue with, but yeah, the implication here is that pink is not helpful. There is no point on the trait where pink is most likely. So it's not helping you measure the trait. It's just adding noise. So if you found an answer category that consistently across items was behaving this way, I might be tempted to collapse. I don't know if there's a way to empirically test which way collapsing would go better. I'm not sure those are nested models, but there might be a way to look at AIC versus BIC, something like that. I'd have to think more
Okay.
about that.
That's what I was going to ask you, but okay, that makes
Yeah,
sense.
there's nothing that's at the top of my head that's like, oh, this is how I do it. I'd have to think about it. Because it's different data sets and anything based on likelihood, like what the highest the data can be is based on that constellation of answers. So collapsing ruins what the data mean in terms of their height. So I'm not sure. There is a, what is it called? The Vuong test, VUONG. That's often used to compare the fit of different distributions. Maybe something like that could be used here, but I'm not sure. You might just have to argue that you like one way better. um, so question about what the plot means. Each line indicates a category, which means different answers. So yeah, so this is an example prediction from a partial credit model, and it is giving you what the probability is for each of these possible answers as a function of theta. So there's 4 possible choices, and the deltas on the plot are giving you the version of this model's locations, but the definition of the location is the point along the trait where the next answer becomes more likely, not just 50%, because 50% is what it is in the graded response model. It's not 50, it's just more likely. So is it okay if we just erase one response? Yeah, that's what we're talking about. So if we look at pink, there is no point at which pink is most likely. So it's hard to argue that even having this choice in here is indicative of your theta, because it's more likely at any other point on at all points on theta that you're more likely to pick something else. You're not likely to pick pink anywhere relative to the others. So yeah, this model can help you diagnose these sorts of problems and how people are using the categories. Something where it's backwards like this is worth taking a look at. How about the thetas 0 and 2, two curves intercept? I'm not, oh, at a theta of 0, that is where the 3 becomes more likely than 2. So the last delta then is how much theta it takes to kick over from 3 versus 2. At -2, that is where pink is most likely, but that's not a model parameter because 0 versus 2 is not in the model. The model is 0 versus 1, 1 versus 2, and 2 versus 3. So there's nothing in the model parameters that directly contrasts 0 versus 2. I think you could work to get what it would be algebraically, but that's not given directly as a model parameter. So yes, this is a reversal. This is where Lisa makes fun of herself again. This is the fit of a bunch of partial credit models from the items in my dissertation. Do you remember that I told you I was all proud of my test information function, even though it topped out at 2, which is shitty reliability? Well, look at these things. So what these actually are showing is response time for a visual detection task where I cut up response time to make an ordinal variable out of it because I didn't think you could fit an IRT model to response time directly. So this is yet another thing that I've learned since then, but they're not going to take my degree away. So I cut up response time into categories, and then I fit a partial credit model to these categories. And this is not good. Basically, the only things that are useful is green, which means they ran out of time and they couldn't find whatever it was, and black, which means they found it in less than 15 seconds. So either they found it right away or they didn't find it. These other blue and pink lines that are just creeping along the bottom here are not helpful. So bad, Lisa. But I wrote it up, I turned it in, and I graduated. And let that be a lesson to each of you. It doesn't matter if your results suck. You write it up, you turn it in, and you graduate. I did end up publishing these results after I had been in my nice, cushy postdoc office for about 9 months. I finally had the strength to open up the project again and try and look at it. So here's some more examples from real data that I fit partial credit models to. So this is a measure of generalized, what is it? Anxiety, I think, if I'm trying to remember correctly. Yeah, I don't have anything on here, but I'm intrusive thoughts. That's what it is. Yeah. So how often do intrusive thoughts, like things that you're worrying about, things you shouldn't be thinking about, but they creep in, how often do they creep in? And so this is a 5-point scale. Strongly disagree versus disagree is your first submodel. Disagree versus neutral, neutral agree, and then agree versus strongly agree. And what these lines are showing, the y-axis is just item, and I have it ordered so that the items are ordered in terms of the location. And the x-axis is the trait. So for instance, for the first item, number 9 up here, the strongly disagree versus disagree distinction, disagree becomes more likely at a theta of -2. So strongly disagree versus disagree happens somewhere around a theta of -2, and the transition at the other end of the scale between agree versus strongly agree happens somewhere around a theta of +2. So the fact that all of these items are spanning 4 standard deviations is why we don't have ceiling and floor effects in the trait distribution. I've got enough information that goes far enough out to where I can distinguish amongst people. But look at the middle. Green and orange are sitting right on top of each other, and sometimes are backwards. So for instance, for number 9, it takes less of a trait to say that you agree rather than neutral than it takes for you to say neutral rather than disagree. So the middle categories are kind of a mess in terms of them being useful for distinguishing things. Here's another one. This is event-specific intrusive thoughts, so a different subscale, but the same type of phenomenon. And this is a 4-point scale. So we have not at all versus rarely, rarely versus sometimes, and sometimes versus often. So can you guys tell me, is anyone here, did anyone major in English or literature? And then like come to the dark side and learn statistics instead? No? Okay. Well, I was hoping someone could tell me what not at all versus rarely. Like those sound like a lot the same. Like not at all is like a softer way of saying never. But can you really say never or not very often? Yeah, the blue versus green. They're in the right order in most cases, but they're really close to each other. And then rarely versus sometimes. That's another one. Sometimes and rarely could be distinguished differently by different folks. Sometimes versus often, people can distinguish those ones. But look at where these item categories are and the resulting distribution of theta. So I've got a giant pile of people at -2 here. That's because I have none of these items that spans a difficulty level lower than 1, -1. So I would need something underneath not at all. I need like a hell no response, or something to distinguish like kinds of no. That would get me to be able to distinguish these people over here. But I also have a bit of a ceiling effect. Sometimes versus often doesn't go far enough. So if I added like an almost always or all the time, something like that, that would hopefully be able to distinguish the people at the top. So I think this model gives you a lot of information about how people are using your categories that could help you decide if the labels you've picked are being used in the way you intended and whether you need to add more. So, all right. Questions, thoughts about that? So if anybody wants to try partial credit models for your homework 5, I am totally fine with that. I don't care what software you use. I can help you figure it out in M+ if need be. Or if you want to use FlexMerd or one other software you're already familiar with, that's fine. But that's an option to you. There is a shortcut version of this model in the same way that there was for the graded response model, where you can constrain the differences between categories to be parallel across items. The rating scale model, it's set up in the same way where each item has an overall location and then some sort of category difference relative to that. So that's a way to cut down on the number of parameters that you're estimating as well. So the same idea here, constraining the differences between categories to be parallel in the rating scale model versus letting them be whatever they want in the original partial credit model. So there's a summary of all the different names and how they go in that. One thing that's tricky about this model is that because it's not cumulative, the data demands are higher. So for instance, if not very many people answer 1 or 2, then you're not going to be able to drill down where 1 versus 2 is on your location with a lot of certainty. Standard errors will be really large. So that's one of the reasons why I think this model isn't used as much in practice, even though it's more intuitive to interpret. Yeah, that's the last one. Okay. Thoughts, questions? Then we just have one more. Okay. And if none of those work for you, nominal. Nominal means, yeah, I have no idea if these things are ordered, or I think that they're not ordered, but actually, the way that I think about nominal models is that they're not ordered from the participant's point of view, but they're ordered from your point of view. So, those of you who've read like bullshit teenage magazines like 17 and Glamour and Sassy and Cosmopolitan and like all those, you're familiar with these? Like there's quizzes in there like, what kind of person are you? Or how good is your relationship? And they have items that say things like, if your partner comes home and they forgot to pick up something from the store that you asked them to get, what would you do? And like option 1 is I would not talk to them, or B, I would ask them in a calm voice to go back to the store and pick it up for me, or 3 is I would ignore the problem. And then you get like your score at the end where it's like if you answered mostly A's, then you're in good shape, and if you answered mostly B's, that's not good, right? Those are nominal items because there is an ordering. You're just expected not to be privy to it as you're filling out the questions. So if you think that certain answers are indicative of a higher trait. So how would you respond to the situation as one type of item if you have, say, a multiple choice item where there's one correct answer, but the 3 distractors vary in how good of a distractor they actually are? Like some of them are more likely to be picked by people who are better understanding whatever the content is. A nominal model can help you figure out like how the distractors are arranged relative to that and give you more information, because if they didn't get it right, it may be helpful to know which distractor they picked. That may inform their trait. Another very useful instance of this model, what is going to be 6B on the website. I did not get a chance, I chose not to do that this year because we're already ahead of time, but I have a link to where we talked about it at my version of this class in KU. It is an amalgam of a nominal response model and a partial credit model designed for responses of does not apply or missing. So a few of you, I made a note in your homeworks about this. Do you remember this? Assuming that you all read my comments, right? You read them and committed them to memory, of course. The idea is that if you have an item that somebody chooses not to answer, the fact that they chose not to answer could be indicative of their trait. Like people who have extreme levels of behavior one way or the other may not want to talk about it. So the model that is described in example 6B, what is it? I forget what it's called. Corinne Huggins Manley is the one who developed this, and so there's code in there to do it in M+. The idea is that you combine a partial credit model for the responses that are ordered with a nominal model for the one that's not, and you yoke them together so that each item has the probabilities summed to 1. So it's a way that you can actually use the information of does not apply or missing data or any other response that people could have given that isn't ordered but is still potentially indicative. So nominal models can be used for those sorts of things too. The way they work is like you're dummy coding your outcome variable. So the submodels that you're creating here ask you to denote a reference category. In M+, for instance, it's the highest reference. And then each of the submodels gives you the conditional probability, like if you picked 3 or 0, what's the probability you picked 0? And if you picked 3 or 1, what's the probability you picked 1? There's another parameterization of this model that I think is less intuitive that makes everything sum to 0. I put up an article on the website. I forget what the Revalte, I forget who, exact person, but it was a Teacher's Corner article in SEM that talked about nominal models, and they went over both parameterizations with a worked example, and there's M+ code. And so I found that article to be exceedingly useful at describing these models and how they would be fit. So I would refer you to that if you're interested in fitting a nominal model. But the idea is the same, though, of everything that we've been doing, where you have your binary submodels. The only difference is in how they're defined. And the one thing that makes nominal different is that there is a separate slope in each submodel. All of the others constrain the slopes to be equal across submodels, but nominal has a separate slope per submodel per item. So a lot more parameters in nominal as a consequence of that. So here is a picture that shows that, for instance. You might have A is the correct answer on a test. B is a distractor that is a better distractor. So people who are higher on the trait might be more likely to pick that, with the other distractors being over here. So just as an example of how that might work. So that's it. Those are the models for categorical data that I can help you with if you're interested. Other models that I have an example of are models for the count family. So if you have behavioral items, things like number of cigarettes smoked or things that are described by count distributions, those can be latent trait model items too. And so I have an example of how to fit those kinds of models in M+. That is going to be 6C that you can look at on the last version of this class as well. So bottom line, no matter what kind of item response you have, you can fit a latent trait model to it. You just have to figure out the right link function and distribution to go with the item. So the thing, for instance, that I did in my dissertation where I cut up response time, I would actually fit a 2-part model to that instead. I would have one submodel be whether or not they found the item before the time ran out, and another submodel would be how quick they found it if that's what they did. That's what I would do now. But 17 years later, I have hindsight as 2020. Ta-da. So thoughts or questions before we call it a day? So how much does the syntax have to change in M+ if we have 2 factors, or would it be easier to do 2 separate IRT models? The syntax has to change in that you would write like factor 1 by these items and then factor 2 by those items. You would have to make sure that each factor is identified. So each factor's mean fixed to 0, each factor's variance fixed to 1. And then you would ask for covariances between the factors, factor 1 with factor 2, and as many covariances as would be applicable. Other than that, that's everything else would be the same. Sure. Other questions? Okay, so in terms of your homework 5, I'm expecting you to fit models to the same data that you did in homework 3, where most of you found that the CFA model did not fit well, right? It predicted responses that went out of bounds. I'm leaving it up to you as to what you want to do instead. For most of you, I think the graded response ordinal models following example 6a will be your best bet. But if you want to try something else, I'm happy to try and help you figure out what else would be available or would fit you. So let me know if I can help, okay? All right, then that's all I got for now. Next week, we start talking about invariance and diff. Hooray! So have a good weekend. Let me know if you need anything. Peace out.